All right, today's topic is refraction, the twin property to reflection. Hopefully, you enjoyed the reflection lab, the video lab. Um, so, refraction deals with the changing direction of a wave. Again, it's interacting with a boundary, but instead of bouncing off the boundary, it enters into the boundary and it bends, it changes direction because light has a different speed in different media. Okay, so a good example of this, if you think back to your childhood and you're pulling your little brother or sister in a wagon and you're running and trying to scare them or having lots of fun and you're uh, changing from a sidewalk to a grass field. And you may have experienced that the wagon wheels will just automatically turn because this wheel slows down before this wheel. And these wheels slow down before these wheels do. Okay, so the wagon will change direction going from a sidewalk to grass. Similarly, a light ray going from air to water will change direction. It will bend as it enters air into water because it's significantly slower in water. Now, with a ray, it really doesn't make that much sense. But if you think of light as a wavefront, then this part of the wavefront will slow down before this part does. And so it will bend. And so you can see the bending of the wavefront, the change of direction of the wavefront as it enters the slower medium. This is actually a ripple tank, and this is the direction of motion. It's going from left to right. Okay, and then here it's going this way. So, refraction of sound. Sound is a wave. It has different speeds in warm air than cold air. So here a bugler is playing a noise and the dog is unaffected because the sound from the bugle is refracted upward. And conversely, the bugle sound is refracted downward and wakes up the dog. You may have experienced this sometime when you're camping at a lake at night. You can hear easily across the lake. You can hear the campgrounds as if they're right next to you. Whereas during the day, the sound refracts the other way and you can't hear. Okay, so here's a refraction of a laser beam going from air. And here, this we call this the incident angle. And then this would be the refracted angle. You can see that the angles are different. And then it's reflecting off of a mirror at the bottom of the aquarium. And then it refracts back. This would be the incident angle. This would be the refracted angle. And then interestingly, this angle and this angle would be equal. And then this angle and this angle would be equal. Now, here's the rule of thumb. When you're going from a faster medium into a slower medium, the refraction is toward the normal. So here we have an obtuse angle, and here it's more acute. So it refracts towards normal. When you're going from a slower medium to a faster medium, it refracts away from the normal. And so all these references, the angle reference point is the normal line. All right, now one of the things I'm kind of bummed about is this is one of my favorite units in terms of demos. There's tons of demos on this. I'll try to get a video of all these demos, but I did go on the YouTube and I found several of these demos for you to see. So when you're looking at something through a block of glass, the object looks closer than it actually is. So if there was a penny down here, the penny would look up here. You may notice that when you look in a swimming pool and you look down at your feet and your legs look really short. Or this person looking at this fish, it sees the fish here where the fish is actually right here. Now, question, if he's a spear fisherman, where should he throw the spear? And he'll see the fish here, but he should know to aim low. This is a glass coffee cup. Glass is fairly thick for a coffee cup, but when you look at the coffee in the coffee cup, it looks like it goes all the way out to the outer edge, which is impossible because there's glass there. But the image of the coffee refracts outward. Things like mirages. A mirage is a refraction of an object um, or the sky. Like right here with this caravan, it looks like there's a lake or a pond right here, but there isn't. All that's there is hot sand and hot air, and the light from these camels and these sand dunes and the sky is refracting off of that hot air pocket. Okay. When you see shimmering so-called heat waves, it's actually just a refraction of the car, refraction of the sky off of the hot pavement. There's a special kind of mirage called a Fata Morgana mirage, where you can see a ship that appears to be floating in the sky. So pretty cool. Now the lab we're going to do tomorrow deals with the index of refraction. And the way to calculate the index of refraction is you take the speed of light in a vacuum or in air as the reference point, and then the speed of light in the material, which is going to be markedly slower. Okay, so the index of refraction is always going to be some amount greater than 1, 1.2, 1.3, 1.6, something like that. Now, another way of calculating the index of refraction is to take the sine of I over the sine of R, where I is the incident angle and R is the refracted angle. So that's easier to measure than this is. So what we'll do in the lab is we'll measure this angle and measure this angle, take the sine of this, the sine of that, divide them, and we'll get an experimental value. Okay, now one of the applications of refraction we're all familiar with. You might call it the production of a rainbow, but the technical term is the dispersion of light. So when you separate light into colors arranged by their frequencies, you see a pretty rainbow, pretty colors. But the technical term is dispersion when it's produced this way. Okay, so there's different ways of dispersing light. We can disperse light by refraction, or later we'll see how we can disperse it by the interaction of diffraction with interference patterns. Okay. So when light is dispersed through a prism or through a series of raindrops, then you get a rainbow. You get a spectrum of colors, Roy G. Biv. Okay. Now, people generally think, oh, it's because of the angle of the prism, which is certainly part of the equation. But something else has to be happening here. What determines the degree of bending other than the angle that it's the angle of incidence? Well, the degree of bending is predicated on the degree of change in speed, which means that red light has a different speed in glass or in a medium than violet light. So go ahead and pause the video here and ask yourself, why would violet be slower than red? Okay, that's really corny. So anyways, the short answer is it has more wavelengths, more interactions with more nodes to interact with the material, the medium that it has to interact with. Okay, so the average speed of violet light is slower than red light, so it bends more. So you get this Roy G. Biv pattern. Okay, so I butchered that, but I think you get the idea. So with all of that, how do we get a rainbow? Well, there's two properties that have to happen. We get internal reflection, which we talked about in the last section. So the light hits the raindrop and enters, and we get light rays from all angles. Okay, but the net result is the light comes in and bends, and then it internally reflects twice, so that the light is now coming back in the direction of the observer. Okay, and so we get two properties. We get diffraction, start over. Two properties. You get refraction, the bending of light, and then you get reflection, which is why the light comes back in the direction towards the observer. So we have light coming in this way from the sun. It hits the raindrop, reflects twice, back towards the observer, okay, at a specific angle. And the angle depends on the color, as you can see. So, where does the sun have to be for you to see a rainbow? So there has to be sunlight and rain simultaneously. And you should always put the sun behind you and look for the rainbow this way. Okay, so why are they circular? Well, it has to do with that angle. Okay. And you may be thinking, no, they're semicircular. Well, the only reason it's a semicircle is that the ground gets in the way. So if you imagine moving this protractor around, and the angle of the rain here is at a 42 degree angle, 42 degree, 42, 42, 42, 42, 42. And so you get this circular pattern. If you were in an airplane, you could see the circular pattern. Or if you're in your yard on a ladder at a certain time of day, and you're spraying a fine mist and looking for the rainbow, if you are able to not fall, then you can also see a circular rainbow. I won't tell you how I know this because it's dangerous. Don't try this at home. Okay. Now, the other day, my son and I saw a double rainbow. So here we have a single rainbow. Here we have a double rainbow. Notice the colors of the pattern, the order's changed. Also notice that the light, the sky is lighter here than here. And the reason for that is a lot more complicated than we have time to go into. But for a double rainbow, essentially you have to get another reflection. So you get a third reflection and to produce the second rainbow. And it's upside down because of that third reflection. Okay, internal reflection. If you were to shine a flashlight or a laser beam in water, most of it's going to go straight out and refract. Some will reflect down. As you make the angle more and more obtuse, the more and more of it will actually reflect. And then at some point, all of the light will reflect rather than refract. That's called internal reflection. This is particularly important in optics. Like in binoculars, there's a prism set up. Spotting scopes, there's prisms set up to invert the image. In diamonds, light comes in from all of the different facets. It internally reflects, and then the only place for it to go is out the top, so it looks really, really sparkly. And humans go, ooh, pretty. I want to pay thousands of dollars to express my love for you with this sparkly thing. Okay, it's also super important in fiber optics. Fiber optics use light to send information, and you can see that the light will internally reflect. So here's the cable, and the light here is coming out the other end.